So now enthalpy of reactant equal to 0. So for the value of Tp which you have assumed, Hp should be equal to 0. Correct? Or when you try to, it can be exactly 0. Correct? So what we can do, we can give a tolerance. Exactly 0 means you have to really fine tune your temperature and get the value of Hp so that it actually goes to 0. So instead, what I can do is Hp, if it is less than 10 power minus 5 or 10 power minus 3 or something like that, then I can stop. I need not go to exact 0. Okay. So what I do is I go to NIST database and get the values of enthalpies of several species listed as a polynomial of temperature or in a tabular form, and use that and get the value of Hp and see whether if Hp is less than, say, a low value, then I can say that that value of Tp what I have chosen is the adiabatic flame temperature. So now in this case what happens? First I assume a temperature of 1800 Kelvin and get the value of Hp as minus 12 kilojoules. When I assume the temperature of 1900 Kelvin, Hp becomes 15.9 kilojoules. So minus 12 to 15.9. So there is a change of sign. So now I can interpolate between these two because it crosses 0. Interpolate between 1800 and 1900 and get the adiabatic flame temperature as 1843. So please see this 1843 will not cause much dissociation of even CO2. So for CO2 to dissociate, it is shown that about 1% dissociation occurs when Tp is approximately 1900 Kelvin. So now when the temperature is less than 1900, say 1843 etc., less than 1% of CO2 dissociates. There is no question of H2O being dissociated for this. But if the temperature goes beyond 2000 Kelvin etc., it is important to consider the dissociation. So this is an example where when excess air is present, then the flame temperatures are not so high, dissociation need not be considered. And without considering dissociation also, you get a realistic value of the adiabatic flame temperature. Let us consider one more example now. Flow reactor, benzene C6H6, which is vaporized. So benzene vapor comes in with a stoichiometric air flow rate. Okay, so C6H6 plus 7.5, 6 plus 6 by 4, O2 plus 3.76 into, giving 6 times CO2, 3 times H2O and 28.2 times N2. Okay, now I proceed with the calculation. What I do first is I take the stringent condition where I don't consider dissociation at all. CO2 is intact, H2O is stable. So dissociation is not considered or dissociation is neglected. Then the adiabatic flame temperature, guessing some values. Again I will guess 2500, 2600. Then for each of this I will try to calculate Hp and match it with the HR. Here, since the incoming reactants are at 298 Kelvin, HR will be equal to HF of C6H6 at 298 Kelvin, only enthalpy formation. Now this should be vapor. You are consider because vapor is sent in. Now go to this. Products, I guess a temperature, say 2500 or 2600, something I will guess. Maybe you need to do more iterations. Say start with say 2300, increase it. Finally, you will find there is a change of sign between Hp and Hp minus HR between 2500 and 2600. Then you can interpolate between these two temperatures and get the value of the adiabatic flame temperature as 2529, which is basically very, very high. When you measure it, it can be 2300 something. So about 230 or 250 Kelvin extra you are trying to evaluate. So that is not correct. So what you do now? Take the dissociation of CO2 and H2O. So what I exactly demonstrated in this particular for methane, consider in the product A times CO2, B times CO, C times H2, D times H2O and E times O2, and considers these two dissociation reactions for CO2 and H2O, and calculate Kp1, Kp2 at the temperature and find the product composition A to E and repeat the procedure. So same thing you can repeat for the benzene. Now if you do this, or you can also do it with NASA CEA, you get a temperature of 2341, 2341. As I told you, this is realistic temperature. What you have predicted is about 200 Kelvin more when you don't consider dissociation. Okay, so this is the important thing. Now if you try to add more and more values of more and more species in the products, instead of only CO, CO2, H2 and H2O and O2, if you try to add more and more, then you can slightly reduce it, say about to 2300 or 2290, something like that. But okay, this is a good estimate than what you got without dissociation. Further, when you do this calculation, I will also find the composition of the products, that is the mole fractions of CO, CO2, H2 and H2O are got as 0.0215, 0.1374. You can see that good amount of CO2 has dissociated, but when you consider H2O, not much dissociation has taken place at this particular temperature. That means H2O requires more temperature to get dissociated. So this is a procedure with including dissociation to get a good estimate of the temperature. Okay. Now, is there any other way to calculate the flame temperature in a more simplified manner? Yeah, it can be done, but there is some procedures to follow. Let us talk about that now. The thermodynamic approach can be used to evaluate the flame temperature using specific heat of the product mixture. The product mixture itself is considered as a single gas and its specific heat can be estimated. But you know that the specific heat is a function of temperature. That means that specific actually varies with temperature as a polynomial. So Cp can be A plus Bt plus Ct square plus and so on. So some fifth order, sixth order polynomial, you'll get something like that. But again, if you use it, then you are going back to the same integration things, and the procedure is not very much simplified. But instead of this, if I take an average temperature and calculate Cp of the product mixture, then my equation is an algebraic equation, straightforward. I can solve it in one shot. So we will try to demonstrate this. So first of all, the selection of the average temperature at which the specific heat of the product mixture can be calculated. That is very, very important for us. Okay, but several thumb rules are available in literature for that. Okay, for heat transfer literature or from fire literature, you can take out several thumb rules or several correlations of calculating the average temperature. So now let us consider again the reaction between benzene vapor and the air in a stoichiometric manner. There is no need to consider dissociation, etc. Now let us consider a complete combustion, 6CO2 plus 3H2O plus 28.2 N2. Enthalpy of reactants and products can be calculated by sensible enthalpy in terms of specific heat now. Okay, so now as I told you, when the reactants enter at 298, HR is contributed only by the enthalpy of formation of benzene vapor. Now, for the products which are at higher temperature, you will see that I have regrouped the enthalpy of formation of this first. Enthalpy of formation of CO2 into 6, that is the 6 moles. Similarly, here it should be 3 times enthalpy of formation of H2O. This is the enthalpy of formation of CO2. 6 times enthalpy of formation of CO2 plus 3 times enthalpy of formation of H2O. Done. enthalpy of formation nitrogen is 0. So this is the enthalpy of formation. So I will say that H0F of the products, enthalpy of formation of products, plus this is the sensible enthalpy part. Correct. So what is enthalpy of product? Is the enthalpy of formation plus sensible enthalpy. Now I have regrouped the enthalpy of formation of the product species which are there, which is known to me, and I just group this. And so this term is known to me. Straight away I can calculate. But in this, the second term, I write as the number of moles of the product which are leaving, flow rate, okay, now kilomole per second into Cp of the mixture. So this is what I am trying to calculate at a given average temperature. So based upon the choice of the temperature, the value of Cp will be fixed. Based upon that, you will get some result. Okay. So now please see this Tp minus 298. That's all. What is sensible enthalpy? The enthalpy associated with heating the product mixture from 298 Kelvin to Tp. So Np, Cp mix, this is actually joule per kilomole Kelvin. Np is kilomole per second. The flow rate, no? So now here you can see that sensible enthalpy is simplified like this. So if I equate now HR equal to HP, I can straight away calculate the value of Tp if Cp mix is known to me. That means in one shot, it's an algebraic equation. In one shot, I can do this. But if this value of Cp mix is not properly chosen, I will not get the correct estimate. So in this, okay, what is Np here? Np is the total number of moles, 6 plus 3 plus 28.2. So Np will be equal to 6 plus 3 plus 28.2. That's it. Total number of moles of the products, 37.2. So whatever equation I have written, I have based upon that. Now Cp mix can be calculated using K. This is what, as I told, joule per kilomole, or here in this case it is kilojoule per mole Kelvin. So this is also the same. So I'll get the kilojoule per mole Kelvin here. So Cp mix is calculated as the summation of product of mole fraction of each into Cpi. So for example, it will be 6 divided by Np into Cp of CO2 plus 3 divided by Np into Cp of H2O plus 28.2 divided by Np into Cp of N2. Now these Cp's in turn have to be calculated at a average temperature. Then you get the Cp mix calculated at T average. So the choice of this T average and this estimation of Cp mix with that will be very, very important. Okay, so now CO2 mole fraction is 0.161, H2O mole fraction is 0.081 and N2 is 0.758. So now I will, what is that now remaining is the estimation of T average. Okay, as I told you, based upon the configurations and the scenarios, T average can be different. So we have to see the literature and make the choice. It is not just a one formula for all the cases. So let us demonstrate this now. So now if I write this in one shot, I can calculate when I equate the HP equal to HR. In one shot, I can calculate TP as this. So it's very simple. So only thing is proper estimation of Cp mix is going to be important for me. Okay, now I make a wrong choice. Let us say Cp mix is evaluated at 298 Kelvin. Obviously 298 Kelvin cannot be the average temperature, correct? The fire temperature can be as high as 1500, 1600 degrees centigrade, and ambient temperature will be 298 Kelvin. So if I assume the average temperature to be ambient temperature and calculate the CP mix, then with that if I calculate the TP using this relationship, I get a very high value, which is not realistic at all, 3050 Kelvin. Okay, the problem here is the right choice of the average temperature is not made. So now I can try to improvise this. Okay, so let us take a choice of 1200 Kelvin now. Specific heat and constant pressure for each species are now calculated at 1200 Kelvin, and the average. So let us say this is typical average temperature. Then I calculate CP at 1200 for each of the species and use the mixing rule to calculate CP mix itself as 0.0381 kilojoule per mole Kelvin. Now I get the temperature of 2500, which is much better than what I got, correct? So now if I slightly increase the temperature, so that's what, based on the configuration, I will have some thumb rules. Please understand that this is an estimation, but if you want to evaluate properly, then you have to go for equilibrium calculations only. So the main advantage of this is in one shot I can calculate, but the CP value, normally what I can do is I can vary this temperature and get a, for a given configuration, I can get a average temperature at which I will calculate. So people have also recommended 1800 Kelvin or 2000 Kelvin also for calculations in certain scenarios to get a proper estimation. But this, what I try to demonstrate here is, when a simple thermodynamic approach, just write in a simple algebraic manner, you get a good estimation of temperature. That is good enough. Even it will reduce the calculation procedures of involving iterative temperature calculation, even when the products are fixed, or if you go to basically the see, this actually is the correct estimation because we have not considered the dissociation in the reaction. If you see, we have not considered any dissociation, and with the average temperature of 1200 without considering dissociation, what I ended up with is 2534, which is exactly the same of what I have got here, 2529. For the same reaction without dissociation, I have got 2529. With the average temperature of 2200 Kelvin, I have got 2534. So that means if you add more species, then your CP mix will be evaluated properly. Even at this temperature, if you add more species, then I can get this. But again, there is some another additional calculation required to get the composition properly. Okay, anyway, equilibrium has to be used if you want to go to more and more final values. Okay, so basically we can say this is a better estimation considering without dissociation and so on, and average CP. Now further simplification can be done if you note the out of 37.2 total number of product moles, 28.2 is that of nitrogen. So nitrogen is too much in the product mixture. So why can't we just take the nitrogen as the primary constituent and get the specific heat of the mixture same as the specific heat of nitrogen, calculate the average temperature? That is also possible. If I do that, then again by varying the product temperature or the average temperature, I can get the estimation of the maximum temperature. So basically there are several procedures to estimate the maximum temperature that can be reached, but we can safely say that the actual temperature will be 200 to 300 Kelvin less than what I estimate by these procedures. So till now we have analyzed the control volumes where the flow of reactant takes place, combustion completes and products leave, and there will be heat exchange between the control volume to the surroundings. Now let us say if I have a system can be a piston cylinder arrangement like this, where there will be some reactants initially, then products can be formed after ignition. Similarly, there may be a rigid vessel, in which reactants to products can occur. So, in these cases, the mass is fixed. There is no mass transfer in and out of this. So, that is we call system or fixed mass. Mass remains constant. Now, in the first case, when there is a piston cylinder arrangement, when there is a reaction, so let us assume that the piston is free to move and the cylinder is long enough, and when the reaction occurs, the piston moves up, equilibrating the pressure. That means a constant pressure combustion occurs. On the other hand, if you take a rigid vessel like this, when you ignite the reactant, products are formed, temperature is increased based upon whatever be the heat transfer. So the pressure can increase in this. Pressure can increase. If you cool it as rapidly as possible, the pressure rise will be lesser. If you are not able to cool it, then pressure will increase in this particular case. So here, constant pressure combustion occurs. Here, constant volume combustion occurs, where the pressure can rise. In both the cases, I can reject heat. That is exothermic reaction takes place in these two, and heat can be rejected out. Okay. So now, first let us take the piston cylinder arrangement. Combustion takes place within this. So first fuel and oxides are present in this at flammable condition. Because if they are not flammable, then we cannot ignite it at all. So at flammable condition, flammable proposition, the fuel and oxygen are present in the piston cylinder, and we try to ignite it. Then the first law for this can be written as Q, whatever be the heat interaction, minus W, any work interaction, equal to the change in the energy E2 minus E1. E is the total energy, which is written as the internal energy U plus kinetic energy plus potential energy. Okay, now please see, kinetic energy of the system is nothing but if the system itself is moving with velocity, it has a kinetic energy of mv square, is where m is the mass of the system, v is the velocity at which it moves. Potential energy is if the system itself is at a particular height from the reference plane, then so that height is say h. So mgh will be the potential energy. But often I don't have these two, so I can say the total energy E will be equal to the internal energy. So Q minus W will be equal to U2 minus U1. So U2 is the internal energy at the final state after products are formed. U1 is the internal energy at the initial state, because U is a property. Q is heat interaction. W is the displacement work. When the piston moves up, there will be a change in volume, increase in volume, that causes a displacement work. So W will be integral P dV. Okay, so that is the displacement work what we say. Okay, so the heat interaction is basically, now we know that in the combustion scenario, heat is released within the system, so that can be transferred out of the system basically. Okay, now how to analyze this? We go to the, when as I told you, when the piston is free to move upwards, the piston rises up. So when there is a reaction taking place, the heat release occurs, temperature increases. So if the piston cannot move up, the pressure also will increase. But if the pressure slightly increases, the piston can move up and equilibrate the pressure inside and outside. So when the piston can rise up, then it can maintain a constant pressure within the system. Okay, now integral W equal to integral P dV can be written as P into integral of dV equal to P into V2 minus V1. That is the volume at the final state minus volume at the initial state into what will be the pressure at which this combustion reaction is taking place. So now I write Q minus W as P into V2 minus V1 equal to U2 minus U1. Now I take this Q equal to this, I take the other side. So P into V2 minus V1 plus U2 minus V1, or I can write as U2 plus P2 V2 minus U1 plus P1 V1, which is equal to H2 minus H1, which is equal to the heat of reaction. So Q equal to delta HR, heat of reaction, which is the H2 minus H1. What is H2? H2 is the final state, enthalpy of the products. And H1 is HR, enthalpy of the reactant. Okay, now in a constant pressure system, the heat interaction is equal to the enthalpy change. Okay, so that is delta HR. That is negative for the exothermic reaction because of the fact that H2, which is the product enthalpy, is less than the H1 or HR. So delta HR is negative. That means heat is rejected by the system or transferred from the system to the surroundings. For the surroundings, it is a heat gain. That is delta H combustion will be equal to minus of delta HR. If the system is adiabatic, then what happens? HP will be equal to HR if Q equal to 0. In that case, maximum temperature, which I have seen as adiabatic flame temperature, will be reached. Do you understand? So this is the first law analysis for the combustion taking place in a piston cylinder arrangement where pressure is maintained constant. Now let us go to the constant volume reaction. That is, a rigid vessel is present in which reactant are initially present and it goes to products. Okay, so since the walls are rigid, the volume is constant here. Okay, the piston can move up, that can increase the volume, but in this case it is not possible. So volume remains constant. Mass of the material inside this also constant, volume also is constant. In the previous case, mass was constant, volume was able to change because of the movement of the, that is displacement of the system boundary. Okay, now in this case what happens? W, which is equal to integral P dV, will be equal to 0 since dV will be equal to 0. There is no change in volume. So delta V will be equal to 0. So I can write Q minus W is dropped now. So Q equal to U2 minus U1 or UP minus UR. That is, U2 is the internal energy of the products UP, U1 is the internal energy of the reactants UR. So here the heat of reaction delta HR, again we call heat of reaction as the change in the internal energy. Change in the internal energy between the final state and the initial state, or the product's internal energy minus the reactant's internal energy will be equal to the heat of reaction. What is heat of combustion will be negative of this. Okay. Now, in order to calculate the internal energy, I use the enthalpy's definition. H equal to U plus PV, or I can say U equal to H minus PV. So UP will be equal to HP minus pressure of the products into volume. So volume is constant here. Pressure of the products, since there is a rigid volume and if there is any temperature rise, the pressure also will increase. So pressure at which the products are existing into volume, so HV minus that. UR will be HR minus pressure at which the reactants are present into V. So now please understand that in this scenario, ideal gas relations can be invoked for the case because the temperatures are higher. So we can say that the densities are lower. If the pressures are very, very high, then we cannot invoke that. But in many cases, we can see that the ideal gas equation of state can be invoked. That is PV equal to nRUT can be invoked, so that I can write PP into V as NP, number of moles of the product species or mixture, into universal gas constant. This is 8314 joule per kilomole Kelvin, and Tp, what will be the temperature of the product. Now UR also can be written as HR minus NR into RU into TR. So you can see that enthalpy comes into play to calculate internal energies. You may wonder why directly internal energy values can be used, but enthalpy measurements are more accurate than internal energy measurements. So see, we can see that the heat interaction in a constant volume chamber is the difference between the internal energies, final state internal energy minus initial internal energy. So internal energy calculations are not so accurate, so we fall upon the enthalpy calculations to do this. Okay, so I will stop here. We will continue in the next class.